Hello everyone, it's October 24th. Alright, let's get into it. 222, I might have done this before. It's very low value on the number itself, so I might have done it before. Alright, let's see, come on. Count complete tree nodes. Oh, surprisingly I have not. Alright. Oh, now I'm more excited. And it's a tree. Yeah, usually I'm more excited about trees. Given the root of a complete binary tree. Oh, wait, it's a complete binary tree, which means everybody has, except for the last one, who can have a left child. Everybody else has both a left and right child. Return the number of the nodes in the tree. Every level, except possibly the last, is completely filled in a complete binary tree, and all the nodes in the last level are as far left as possible. You have between 1 and 2 to the h nodes inclusive at the last level h. Design automated runs in less than O(n) times complexity. Given a root of a complete binary to return the number of the nodes. The tree is guaranteed to be complete. Just you want to count how many nodes are in the tree, right? Well, what we do know is if we know the depth, right? If we know the depth, because it's a complete binary tree, so let's say the total depth is, it says, right? It can have between 1 or 2 to the h. So if this h is 0, h is 1, h is 2, right? So if we know the depth of the tree, so we go the depth of the tree, then it is guaranteed that the value we have found, so what we can do, we just go left, and then go all the way left and go all the way right, right? That we can achieve the depth. If the left and the right have the same depth, because it's a complete binary tree, the total value will be 1 plus 2 to the 1 plus 2 to the 2 plus all the way to 2 to the h, the height. What is that? I think there's a formula for this. I forgot. It's a 2 to the h plus 1 minus 1. Is that what it is? Let's see how many this one has. So yeah, if h is 1, we say it's 2 to the 2 minus 1. That's 3. 1 to 3. If h is 0, 1, 2 is 2, then we say 2 to the 2 plus 1, 3. 8 minus 1 is 7. So 1, 2, 3, 4, 5, 6, 7. Yes, it's 2 to the h plus 1 minus 1. That's the total number of nodes given a height of h. That's completely filled. So we go to the left and we go to the right. And because it's a complete binary tree, either left equals right, and then we get the h immediately, or left is 1 larger than the right. And then we know there's something in the last layer. But we need to count the number of nodes in the last layer, right? How do we do that? Well, we can, we cannot. How do we count the number on the last layer? That's a good question. How do we count on the last layer? And we don't want to make it have less than O(n). O(n) is simple, but less than O(n). And then it's a complete binary tree. What is a complete binary tree? Then everybody is a complete binary tree. All right? Yeah, everybody is a complete binary tree. Like, can I learn the depth? But you cannot do the depth of each node. Hold on. I can know the depth, right? I already know the depth. This depth on one side is depth is 2, on the other side depth is 1. Okay. Let's go all the way to the right. Then we know depth is 1. Then what? Or man, if I go all the way to the right, and either I end up with, so if I go all the way to the right, because it's a complete binary tree, so no, it's a complete binary tree, what's gonna happen is if we go all the way to the right, then we know which is the minimum possibility, okay? Yeah, that is the minimum possibility, so we can compute the total number, but we have something remaining, the last level. How do we handle the last level? How do we handle the last level? Hmm. Like, let's say we go all log n to find the level that everybody's filled, right? And then we'll go to that level. But if we go to that level, we are essentially, yeah, we cannot, right? If we go to that level, if we go to that level, huh? Number of nodes, node value. I don't think we can. I don't think we can rely on node value. If we're on the left side, it doesn't matter, right? If we want to find the last level, we have to traverse every single one of them in order to get to the last one. I don't know, man. I'm pretty sure if I write an O1 solution, then timeout. It's not necessary. I mean, if we go all the way left, right, we just want to know where the last node ends. So we go all the way to the left, and then we check the left and right, and we also know the total length. And we check left, and we check right. And then we do have, and then we go check left and right. I mean, okay. So there's one way that it's less than ON. I mean, ON means you have to traverse every single node, right? But what I do is I just always go left. Now we go left first, left. So it'll be left, root, right? So left, root, right, until we find a case where there is no right. Okay, I'm gonna do it this way. We traverse right first, right all the way to the end, and we count the height. And then we traverse left. right? We traverse left, and then we can just go all the way to the end. And once we go to the end, we're going to compare the height to the height we got from traverse the left and traverse the right. If the two is the same, then we immediately return. So we know the value immediately. That means it's a complete binary tree. Got to be a name for it. I forgot. It'd be a complete binary tree. But if the left is one level, it can only be one level larger than on the right side, that means we have to find somewhere right on the bottom. So when that happens, then we just have to go back. We check the right, and then it's good. We go back a level. Oh, so we go back a level. Now we have to look for this one. Yeah, we go we go back a level, and then we can traverse down to the bottom again. So at every single one, at every, let's say, H level, we have to see if I have a left and right until we find one that does not have right. When we find one that does not have right, and that's the end. Okay, if you say so, if this is how it's going to be. Man, this just feels... And we have to go through every single node in order to find this. Right? And then it is all like, okay, maybe like BFS, but layer by layer. You don't have, because the DFS is the same thing. You have to go through. Well, actually, DFS is not. If I only have this one here, right, and I can immediately return, I don't have to go through any other things. And then I just go back a level, down, right? If it's good, back a level. Yeah. Because all the purpose is to find where on the last level we have only one left. Okay, let's follow this idea. How am I going to implement it? So traverse on the right is simple, but then the traverse on the left. So we're going to keep going until we don't have it anymore, right? So once it's a no, then what do we return? Right? What do we return? Interesting question. What do we return? Return one. Like if one does not have left and does not have right, and that's a root, right? That's a root. That's a leaf. That's a leaf. And then we count it. Now we go back, and we check on the other side, and hold on. What are we looking for? No. Once we know on the right side the depth, and we go on the left, all we need to do is to locate the node of the same level, and we ask if it has a left and right. If it does, we don't have to traverse. We just go back. Again, the same level. If it has a left and right, go back. We count how many of those nodes are, and then, yeah, that might work. I would say that's slightly less than ON. Yeah, give it a shot. Yeah, I think it's less than ON. It feels less than ON. At least if it's a fully complete tree, then it's definitely less than ON. So, oh no. All right. So first things first, we're gonna do. Oh, how are we gonna do? Actually, we don't have to DFS if you want to find the height. So we're gonna find the what do I call it? We're gonna call it h, right? H gonna be 0, and node equals root, right? While node.right, node equals node.right, h plus equal 1, right? While node.right, I move here, so that is level 1. And while node, boom, out, that's 1. So h, now we get, that's the longest. Now what we need to do is go on the left side, right? On the left side. So how are we going to do it? We're going to go all the way left, and keep counting the level. So once we reach level h, we're going to say left and right, okay? So that's DFS. Have node level. Node is going to be a tree node. Level is going to be an integer. Do we return anything? We can, but I'd rather say self dot. We want to count the number of nodes that have the last level. So we're just going to say final level leaf. Num leaf. Yep. That's it. Num leaf equals 0, right? So this one we don't return anything. So now we go. Where do we go? So first we say if level is smaller than h, right? If smaller than h, then we say DFS node.left and DFS node.right, which means if it's smaller, we haven't reached the level yet, we just always go left first. Once we finish, we go right. Else, this is elif, more explicit, level is equal to h. Now when level is equal to h, and that means we find the last level. Then we're just going to say if node.left, if node.right, self.numLeaf plus equal to 2, all right? Else, will that one be the first one that we encounter? Yeah, that's a question. So if we go left first, we always go left. Once we finish, then we go right. And we go right, then yes, that will be the first one we encounter. The first one we encounter that we shall return a Boolean value, right? So if this, then we return false, right? That means we have not found the end, right? Else, if a node does not have right, or let's make it more explicit. If node.left and node.right, if node.left and not, yeah, just node.right. If we do not have a right, then self.numLeaf plus equal 1 and return true, right? Which we don't need to do this, we can just do this. And here we're going to say if here's the left returns hold up. If let me think again. If node.left, then we increment. Hold on. If node.left, self.numLeaf plus equal 1. All right. If node.right, self.num plus equal 1, then return false. We have not found the end. Else, if not node.write, then we return true. We have found the end. So false means we need to keep going. True means we found the end. So again, if this is true, which means we have found the end, then we return true. Well, we found the end. If not, we not found the end, we go here. If this is true, then we return true. We found the end. If not true, then return false. All right? So basically, if this or DFS node.write, any one is true, then we found the end. Otherwise, return false, which means on my branch, we have not found the end, so we have to find somewhere else. Otherwise, if it's the same level, then we do node.left. If we have left, we increment the leaf, and then we check node.right. And we have it, and then we have said we have not found the end. But if there's no node.right, then we say we have found the end. Okay. So, special occasion. What if it's a complete tree? We're gonna go node.left, node.left, node.left until we hit level equals this, and then will be no left, no right, return true, and that return true. That's it. Yeah. So what we're gonna do is we're gonna say DFS root level is 0, right? So we do DFS this, gonna populate this, so we're gonna return 2 times height plus 1 minus 1. That's the total number of the complete and plus self.num leaf. All right, let's try this one. Let's see. Missing one required level. Oh, I forgot the level. So if level is smaller than h, then we go also to level plus 1. Level plus 1. Okay. I forgot the level. Invalid syntax. I forgot the comma. None type has a right. It's empty tree. While node and node.write. No, it's actually while node. Come on. While node equals node.write. Yeah, I don't know why I say it should be while node. Same issue. How? Now, what if the initial root is empty? If the root is empty, level is 0, then we go here, and seems like I don't know. Hold on. I feel like I don't want to treat the special case like special. I think we need to program a little bit more smartly. All right, so this is fine, and then here let's do the other way. Let's say, but then how do I know if I've reached the end? I mean, this is on the premise that node is not empty. If the input root is empty, right, then what do we do? If the root is empty, h will be 0, and then this one will not be right anyway. Makes sense. Do I start h as -1? right? We start h is -1. If not root, then that will be 0, because that is a 0, right? How about here? Well, we can say if node is null, we can do like this. If root, then do this. Like this is a contingent on, yeah, because I passing 0, which means I think we have a root. If we don't have a root, then it's all a null point. All right, it's all a null point. Which means, let's just do this. If not root, return 0, right? And then everything is based on there is a root. Like we think at least there is one root. Yeah, although I don't want to handle the special case separately, but it seems like that's the easiest way to handle the empty tree situation. Oh, we still have this issue. What? What in the world? Which test case? Hold on. And the first one is wrong. Let's see. So if not root, and then blah blah, root this, while node equals node all right. So node is here. Oh, I think we're adding one more on the h. H is started with 0. Because I already think node is good. So yeah, I think it should be node all right. On node all right, I move here and then I increment, right? So come on, I have 0. I say I'm at 0. I already know. So I check my right. I move it. I increment it. That shall be right. Yep. That could be the reason. There we go. All right. So let's have a little bit more fun. For instance, 6, 7. That shall be instantaneously, right? Or we can do 8, right? Just 1 sticking out. Yep. Okay, let's see if the runtime is good. 84. It's not too bad. It's not too bad. It's not too bad. But there's one thing I don't know is how fast it's going to be if we do the traditional way, right? So I think I'm going to write another traditional way, just kind of compare. All right, so this is this solution runs in on worst case scenario, but o log n in best. In best case. So worst case is that the last level has one fewer node, right? One fewer node to make the tree a perfectly complete binary tree. The best case is a perfectly complete binary tree. So the idea is to first go all the way, right, all the way down on the right branch. This tells us the height, right, the height of the tree, right, the height of the tree, height of the tree probably minus the last level. And then we go, then we perform the regular DFS, stopping at the height of the tree h, stopping at height h. Then we probe to see whether any node at height h has only one child. Once that node is found, we are done. Right? We are done because we have counted. We probe to see whether any node at one more step. Now we probe to count, right, the total number of leaves. We stop when we encounter the node that only has one leaf. Thus, depending on how far to the right that single child node is located, this algo can thus the farther right, the farther right the single child node is located, the closer the complexity is towards O(n). Goes from O log n towards O(n). I don't know what type of complexity to give it, so I'm not going to give it, but I'm just going to record it. It's going to be 84 milliseconds or a 65% ranking. But I'm just curious. So I'm going to write another one. So I'm going to write another one, which is just a pure. So let's do pure. This is a pure DFS, right? So I'm going to count. I think we can do it as simple as if not root, return 0, and then we're going to return self.count nodes root.left plus self.count nodes root.right and plus myself. I think this is the pure DFS. Let's see. Let's see how fast this one goes. Maybe it's faster than this. Who knows? Yeah, it's the same. It's the same. So it's the same. How about pure BFS? How come the smaller? I thought this one is smaller than O(n). This is like any single, whatever case, it's going to be O(n). This is some case will be smaller than O(n). Some case will be closer to O(n). So I think this does satisfy the requirement. Just for the law, how we do the BFS? Well, BFS will be how do we do BFS? Well, if not root, it turns 0, and then Q equals root, right? And self.rest equals 0 for a while. Q temp is this for Q self.rest plus equal to len Q, right? Temp is this, and then for node in Q, if node.left temp.append node.left, right? Node.left, if node.right temp.append node.right, and then q equals temp, and then return self, return res, self.res. Wait, why do you do self.res? There's no self, there's no function, it's just res. Yeah, this one shall be good as well. Yep. I'm telling you, probably also 84. Oh, it is slower. Slightly slower. Alright, anyway, let's take a look. So we go here, and we go to discussion. Let's see what other smart ways other people have come up with. Yeah, there is a smarter way. Only 18 test cases. That's why it's so fast. Hmm. I see. So we're doing it in the DFS level, right? So at each, okay, I think I know what it's trying to do. So it is at each level, we're gonna go left and we go right. Each node we treat it as a tree, and I go all the way left, all the way right. If they're the same, then we immediately return. If they're not the same, then we have to go left, right? If, from my perspective, if my left, all the way left is not equal to all the way right, then I go to my left, I go to my right, and I see what this one's doing. I see what this one's doing. I think it's similar idea, right? But my implement, now this one is slower if you think about it. Yeah, because it makes sense. It makes sense. So yeah, I did capture the left and right, right? I captured that part. But what I did not capture is I only do the left and right comparison for the root node, but I shall do it for every single node. Makes sense. Makes sense. Should do is every single node, which means if not root, return 0, right? That's fine. And we just go left and right. Say node equals root while, so height h left and height right both start with 0, and then we're gonna say while node.right, node.left, node equals node.left, h left plus equal 1. All right, now do the same thing. The same thing for node.right, and then h right. And we say if h left is equal to h right, then we immediately return, right? We return 2 to the power h left plus 1 minus 1. And we're done. If not, then we return self.count nodes root.left plus self.count nodes root.right, then plus 1. Because I cannot know, so I have to go to the left side, go to the right side, and then do it again. Let's try this one. See how this one goes. Yeah, at each level, right? At each level, we try it, right? And if it's done, then on that level we're done, and then we try on the other level. Oh, shoot. Okay, so 7. There we go, 7, 8. Let's see. Yep, try it. Let's see how fast this one goes. Nope, this one is slow as hell. This one is slow. Why? How come? I try all the left, I try all the right, and if it's done, then we don't have to go. I return immediately. Otherwise, if they're not the same, if all the way left and all the way right is not the same, then I go left and right. Yeah, this one. Aren't you just copying this and even make it slower because you have to go all this step? No. That's not the thing. That's not the case. Hold on. Nope. I don't think I got it. Okay, let's see. That's not the case. Let's read the answer again. That's not the one I see earlier. Come on. Did they just give me a random one? Yeah, this is the one. I do that. If else. How is this different? How is this different? Right? How is this different? I do the left count, right? I do the left count. I do the right count. I say if they're the same, then we do this. If they're not the same, then I do the left, the right, and plus 1. How come this is not faster? All right, let's see. Main solution. Height plus count nodes, all right. Otherwise, wait. This is the height. We go all the way to the left. So we get a height, and we say if height is smaller than 0, we turn 0, that's fine. Otherwise, we say we go root our right. And if root our right equals h minus 1, root dot right equals h minus 1, then it's going to be plus count nodes root dot right. Otherwise, it's going to be this count nodes root dot left. Can be found by just going left. A single node has 0, blah blah blah. Otherwise, the height of the right subtree is just 1 less than that of the whole tree, meaning left and right subtree have the same height. If yes, then the last node on the last tree row is the right subtree, and the left subtree is a full tree of height. You can take that many nodes on the left subtree plus the 1 root plus the number of the right subtree. If no, then the last node on the last tree is the left subtree. Wait. I don't understand. Well, first, I don't understand why this one is longer, right? That's one thing I don't understand, why this one's longer. It doesn't make any sense. I think this one should be faster. But what he's saying is, we're going left, right? And then we go right. And we say, if the right subtree, oh, see the trick. Did you see the trick? Did you see the trick? I always go left. So we always find the height of the tree. So, okay, let me think again. So we go left subtree, right? So we start to first go the left subtree, we get a height. And then we go to the right subtree, we also get a height. We not go all the way to the right. That is the key. We don't go all the way to the right. We go the left as well. And we say if the left subtree height is the same as the right subtree height, then the left subtree is a perfectly complete binary tree. I don't even know what's the name. What's the name of like a perfectly complete binary tree? Is that even a thing? It's just complete binary tree. It's a perfect binary tree, right? I think that's it. A perfect binary tree. Yes, it's a perfect binary tree. I call it perfectly complete. That's just a perfect. If I have a perfect binary tree and a complete binary, so it's a perfect. It's just a perfect binary tree, and that's it. And then we don't have to have a complete. Right, you have to fit. Yeah. All right, I think I understand. So let's now look at it. So what we're trying to say is, we go the left subtree, and we go the right subtree, but we always find the height, right? The actual height of the tree. If the left subtree has the same height as the right subtree, then whatever shenanigan that might happen is going to be on the right side. It's not going to be on the left side. So the left side, we can return its number of nodes immediately. If the right subtree is smaller height compared to the left one, that means the right subtree must be a complete. Then we go on the left side. Nice. Well, I thought this one will be good, but this one is not. I don't know why. Oh, this one is slower, all right? Well, I thought this one would be faster because we are actively counting. Well, actually, no. Yeah, this one is slower because actually I don't know why this one is slower. Yeah, I don't know. It doesn't make any sense because I didn't go down to every single round. This is like O1 login, right? Probably O1 login and login, because at every node we're gonna do O login to get to the height. At every node we get to the height. But this is not good. All right, let's do the actual good one. Oh, and by the way, the difference between these two, right, is 94 and 84 milliseconds. I think that's a case that recursion is actually fast because we use the internal, right? This BFS will use external. So some say like recursion has overhead. Sometimes I think the overhead that's going to be incurred is handled by the language itself. So it's going to be better actually than you implement yourself. All right, this one is the real one. This is the real deal. This is the real deal from Mr. Pochmann himself. Let's post the link. Yeah, he's a genius. Like this type of genius, like even if I practice so much, it just doesn't. I can't reach it. The genius level. All right, so this is the real deal. What happens is we compute, right? We compute the height of the tree at each subtree, right? At each level, no, at each node. But this is a real height, right? This is the real height, which means we always go as a real height, which means we always go down the left branch, right? We always go down the left branch. That's the difference. But what I did earlier is I go the left branch and I go the right branch. So like I was just trying to see if a subtree is perfect, but that's taking more time because I'm not once they're not the same, I have to keep going every single node. But here, we're doing the height. We always go the left branch, right? We're going the height of every single tree, and then we can compare the height. Yeah, that's the genius part. Now, if the height of the left subtree and the right subtree are the same, actually the heights are the same, that means the left subtree is not complete, it's perfect, right? It's perfect. So we don't have to worry about the left subtree anymore. Yeah, that's the genius, left subtree anymore. And recurse on the right one instead. Similarly, if the height of the left subtree is one fewer than, no wait, that's the right subtree, is one fewer than the left subtree, that means the right subtree is perfect, and we only need to recurse on the left instead. So that is the time saver because we're splitting, right? We're splitting, and that's why the runtime is O log n squared, right? O log n squared, because at each level we need to go O log n to find the height, and there are log n levels at most we have to go through. Not really log n levels because we're splitting, so we have to do log n times splitting. That's why it's O log n squared. All right, let's write it. How do we write it? We do need to know, so we do have to, and let's just follow Mr. Pochmann's solution. So we have to have a height, right, which is given a node, and we're going to return so given a node, we're going to return an integer, which is the height. So we say if not node, we're going to return 0. Otherwise, we can always go down the left branch, right? Hold on, this is not gonna be recursion, right? We're not gonna be recursion, so it's just gonna be, let's do it this way. Let's say height is -1, and we say while node, right? And we're always going to go down the left branch. So node equals node.left, and height plus equal 1, and we're going to return height. Right? So if it's an empty node, height is, node is not going to be empty. Okay, node is not going to be empty. So if not node, return 0. That's perfect. If we have something, then we go to the left. Perfect. So this one gives us the height, right? Now, next one's def, this will be DFS. We're going to have a node, and this one's going to return int as well. So this is to find the total number. Again, if not node, that's going to return 0. Right? Otherwise, we're going to find the current, we're going to find the height of the left tree. Now, shouldn't I do the left, right? So we're going to say height of the left tree equals height node.left, and height of the right tree equals height node.right, right? So we find the left height and the right height. Now once we find it, we say if height left is equal to height right. So the left height is equal to right height. Then we're going to say we're going to return, because we already know the left side is perfect. So it'll be 2 to the power height left plus 1 minus 1. That's the total number of nodes on the left side, plus DFS node.right, because we don't know about the right yet, so we go on the right side, and once we're done with the plus 1. Else, well, h left is not equal to h right. That can only be left is larger than right. So we're going to return DFS node.left, right? We're going to go to the left side, find everybody on the left, plus the right side, we can directly say plus 1 minus 1 and plus 1. And we're going to call DFS root. Now return DFS root. All right, let's try this one. I mean, it's a different implementation compared to Pochmann. Pochmann's like, what, 3 lines? Yeah, that's what he likes to do. Let's see. Nope, is not correct. I think it must be the height computation is not right. Let me see it again. No, dot left. Let's see, this is my height computation, right? So we're passing a node, which is going to be the root. And I say node.left, so I can pass in this one. This one shall return 1, right? And then while node, node equals to node.left. H is 1. While node again. Here's the case. Node.left. Because I start with 0, which I have this. And node.left is, we move here, but we add 1. And node.left, yeah. So I'll try this one, node.left. Nope. Nope, nope, nope. Well, node.left. I already say if not node, I return immediately. Okay? And then that means I have a node and I can do node.left. Oh, because I did not check. Because the height of a tree has to be, the node has to be non-empty in order for this to return 0. Now I see. Now I see why he has a -1 option. I see. I see. But I don't like the -1 option. So this one, the node has to not be empty when I come in, which means on the height. What if I don't have a left, or I don't have a right? What do I do in that case? Well, let me think. I'm a node, right? I look at my left, and the left is, what if we go -1? Yeah, what if we go -1? I think it's perfectly normal if we go -1. Like, the height can be -1, because if we put -1 into it, -1 plus 1 is 0. 2 to the 0 is 1. 1 minus 1 is 0. It means we can actually handle -1, which means if we go still while node, but we turn this into -1, then if there's an empty node come in, we can return -1, which means the height will be -1. And if the height is the same, then node, all right, this one will return 0. This one is 0. Then it's just myself. You know what? This might be the case. Let's see. Yep, look at that. Look at that. I think this one has it. Yes. Yes, this is the one. This is the one. This is the one. All right, I might have a little bit more comment to make here. So note that we designate -1 as the height of an empty tree because, yeah, we have a because the formula to compute the total number of nodes in a perfect tree stipulates. How about stipulates that when height is -1, the number of nodes is 0, right? Is 0. It's very fitting, right? It's very fitting for our use case. Yeah, we just designate -1 as the height of the empty tree. Therefore, we can handle an empty node coming into the height function. And this will just come out as -1. And we don't care because if it's -1, this one evaluates the 0. I mean, we could just remove this and this, but I decided to leave it here just for readability. You know what? Actually, for readability, it will be better to do it this way, right? It will be better to do it this way. So we have a mirror, like these two are mirror images. So we're basically doing the exact same thing, just depending on different height of the left subtree and the right subtree. Yep, that is the case. All right, we did pretty well today. And yesterday I practiced a problem. Actually, I'm going to put it up right now. So we're done today. I uploaded. So yesterday I ventured out to something that I've never done before. It was quite interesting. I might actually do it again, but probably not today. Ah, come on. Stupid speed. So yesterday I did a question on concurrency, right? On concurrency, I was trying to find if there's anything related to distributed computing, because I'm starting to get a bit interested in that. I mean, the study, the things I research in has a tiny little bit of distributed computing in it, but they don't have. The only thing they have is concurrency. So I did this one. It's an easy question. It's just like kind of practice for concurrency for threads, right? Basically, it's handling threads, and this is a very good problem very simple, very easy problem to handle threads. So the premise is very simple. You have 3 functions. Well, print out first, second, third, but you don't know how these 3 functions are called on the threads, right? You don't know the scheduling, you don't know anything. So basically, you need to implement some locks some semaphores, some kind of mechanism, so that the function, when it wants to print a second, it has to wait, right? It has to wait until the function print first to print. And of course, if you print the first one, you need to send out signal to second, so second can print. And of course, when the second is printed, it needs to send a signal to third, so the third can print. So it's a very simple one, but we have a marvelous post from this guy. 5 different Python threading solutions. So before yesterday, I know this. This is all something I've used in the past to handling, it's actually not threads, handling multiprocessing. I've learned about semaphore. I have learned about lock, but none of the other things, right? So I took a bit deeper dive yesterday into every single, so I implemented every single solution. And boy, this is a joyful ride to understand different tools to handle threading. I mean, Python is not known for threading. I mean, typically, when technically speaking, it doesn't have thread. It only have one thread because of GIL. But they're trying to remove GIL right now because they want to make Python a bit faster. But anyway, right now we still have GIL, the lock, the overall lock. So the threading is like it's kind of fake concurrency, but the library is actually quite good. They have all these kind of tools, and they're quite useful. Like for this problem, each tool it appears similar, right? It appears similar, and it's because it's a simple question, but they do have different use cases, and yeah, it's overall it's good, right? It's good. It's sometimes just break out of the comfort zone and go for something that really challenges you. I mean, and also the documentation. The documentation on Python for all these tools, it's very, very well written. I mean, I did some. I was developing some. I was working, not developing, working with Google Cloud functions on Firebase, and trying to test them. Oh boy, is the documentation. Okay, I'm not gonna say terrible, but it's subpar. I mean, reading that documentation just get me so frustrated. But reading the documentation on Python's threading library, it's a joy. It's quite joyful. So anyway, just on that. So if you look at the problems, let's see if I can go back to the problems. We have not that many, but I think I might be able to go through a few more. I think I'm going to do one more today, maybe later on, do one more today. Look at this. We have print full bar, alternatively print 0, even, odd. Yeah, that's interesting. And of course, these probably are more interesting problems that I cannot do. All right. Anyway, so that's that. And Manchester United lost big time today. Terrible. All right. I'll see you guys tomorrow. Adios.